Hey, it's a quick video here about finding the quartiles and the median. And we're going to start with a few different data sets, different sizes. And this first one has 8. So n stands for the number of, or the amount of numbers in our data set. So here's 8. An example where it's even. We can split the data like this visually. So we have some sort of middle point, which is between two numbers, between here. And just a quick talk about the median itself, or the quartiles. You're going to be splitting data by the actual numbers into 4 groups. So quartile 1 is located on the first 25%. So all of these are 25%. Quartile 2 is the middle, and quartile 3 is the top, representing, let's do it up to a point, so 25%, 50%, and 75% of the data. And so when we're looking at numbers, if we only had one number, it's hard to talk about the quartiles. It's just one number. What's the number right in the middle? Well, technically we could say the median was this, but how can you say it's the middle without things around it? So maybe at least 3. Maybe we look at a case where we have 2. We could possibly say we had the median, which was in between these 2. So maybe the minimum number we can have is 2. So, I don't know, 3 and 10. And the middle would be between them, so 6.5. Then if we obviously move on to 3, we've got an obvious middle, but where do we have our quartiles? Now, technically they could be in between here. But it's hard to see in these situations. It's much better to have a look at larger data points that, larger data sets that have a better number of points. So this is a clear middle. And on the left-hand side, we could say our lower quartiles between these 2. It's still not clear what's the minimum number so that the quartiles are all having a whole number in the data set. Well, we need 1 in the middle, and then off either side we need 3 so that we can say we have a middle one. So the minimum number to give a really nice answer is the 7 here. So what does a quartiles look like? Let's do it with 7 numbers. The one in the center here is quartile 2. The number on the left here is quartile 1. And this one here is quartile 3. Now, how did I arrive at that? Pretty simply, the middle one is definitely the median. And we look to the right-hand side and we have 3. We look to the left-hand side, we got 3. And it's like finding the middle of the middle. Like we found quartile 2 there. We have 3 numbers and it's the middle one, right? So half of a half is a quarter. So this is the ideal situation. Obviously, they're not always 7. So we're going to look at what happens with different ones. With n equals 8, we have, first of all, the median, which we can split to here both sides. So we've got 4 on either side. The median was obviously lie in the middle there. How we find the middle of 2 points, we add them together, divide by 2. So that's 27 over 2, which is 13.5. We can write off the side there, I suppose we'll write quartile 2. And there is a formula, there's a way of doing this without the visual, which we'll get to. But let's say we've got the median in the middle. And either side we've got 4 numbers. We have to find the middle of those to find the upper and lower quartile. So of those even numbers either side, we have to go in between these 2 and in between these 2, because we're splitting them like in half again. And this therefore will be quartile 3, quartile 1. We already found the median in the middle, quartile 2, to be 13.5. And the quartile 3 now is going to be 18 plus 21 all over 2, which is 39 over 2, which is 19.5. You could do that as well by finding the difference between them, which is 3, and then halving that and adding it onto 18. Let's do that for this one. The difference between them is 2, half of it is 1, add it on, and we get 8. But you could probably find the middle is 8 from some numbers that are that easy. So that's how we found the quartiles. It leads to a really important measure called the interquartile range, which is extremely good in finance and a lot of different things because it's unaffected by extreme values. And that's a good reason why we use the median in general. And you could have, say, 3, 7, and 200. And the mean, like the median, would be 7, even if this was 2,000 or it's 20,000, it would still be in that middle position. Whereas if it was, so let's write that again, 3, 7, and 2,000, if you were to find the mean, like the mean average, where you add them all up and divide it by n, you're talking something like 670, let's say, roughly. And that's crazy. It doesn't represent any of those numbers. It's too far away from 2,000 and it's way far away from 3 and 7. And so the mean is probably not that good. Whereas if we chose the median, at least it represents the 7 and the 3 pretty well. So it avoids some skew. So in the same way, because these quartiles are based on that principle, they're pretty solid methods. So what is the let's write it out fully. Interquartile, let's do it properly. Quartile, I don't take it for granted that anyone knows how to spell it. Range. And we shorten that to IQR. And that's going to be the upper quartile. Subtract the lower quartile, which is 2 down to 11.5. And it's a measure of like a range, how spread out things are. But interestingly, it contains 50% of the data, which makes it a very strong measure and something people listen to. Quartiles are very interesting things. They were popularized by, I think, Tukey, if I remember rightly, and essentially for that reason, that they are very easy to work with. They don't have much skew because they're affected by extreme values, but also the representation as a box plot is quite powerful, and you can talk about skew with the box part of it. Right, so we've seen a lot here already. Let's apply some of those same principles to the next data set, which is 7 in here. So this is what it looks like when there's an odd amount. We've already looked at that. We know that the very middle number is the median, it's 14. And then just to show, either side you have 3 numbers that are left. And so the middle of those are going to give us quartile 1 and quartile 3. We really like it when this occurs, but how often does it occur? I don't know. Not too often. And we can then find the interquartile range, which is 20 take away 8, 12. It's the best scenario. Now, it might be a good opportunity to talk about an alternative way of getting there. When we get to example number 4, actually, I'll wait till. Right, let's look at 3. So, yeah, number 3. We're talking about 10 and 50, and it kind of makes not much sense. We've already had the discussion about what happens when there's 1 number, when there's 2 numbers. Okay, we could probably find the median. Okay, so I'm happy to do that, which is 10 plus 50 over 2, which is 30. So I'm happy to sort of endorse the median as 30, kind of. The quartiles won't make any sense. There might be some people that say it's 10 and 50, but I'm not going to go down that road. I'm going to say it's kind of nonsensical. As with all data, you need a certain number of data points to do stuff. And you really don't need that much to do these, but you need at least some. And we talked about it's possible to find quartiles like in a nice way with 4, I would say. Because you know you've got your median in the middle and you can find a midpoint of 2. Like you need at least a comparison, I would say. So I think 4 is the minimum here. So we're going to leave it like that one. And be brave enough to, I suppose, to say, well, I can't do the method here. And that's okay. Example 4 is a good chance to look at a different way of doing it without counting or using it like drawing lines. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I had a very strange set of numbers, but to me it didn't matter. You've got 20 numbers, right? So n equals 20. And this is a case where we have an even amount, so we're going to have something like in the middle. But in this case, I'm going to look at a way of jumping straight to something. Let's say we knew we had 20 numbers. How do you define the middle number? Is it number 10? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it this one? Well, one last indulgence on the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got sort of 10 numbers either side here. 10 isn't the middle. Like, you can't just say that the 10th number is the middle. It's not half of the 20. And we know it's in between the 10 and the 11. So what we do when we have a data set like this, like 7 numbers, we add 1 to the amount of numbers that we have, and then we half it. Let's see it work. 20 add 1 over 2. That's 21 over 2, which is the 10 and a half number, like 10.5, 10 and a bit. I always like to write that this is a position, because this is a formula for finding the position of the median. So how does this work in principle? Well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we're talking about the 0.5 representing the midpoint of the next. So that would be 10.5, which is very strange, because that's also, well, it's just because I've used the numbers 1 to 10. But yeah, awkward. So then we've got the job of finding the quartiles, which is a very similar way. So we add 1 to it as usual, but because we want a quarter, not a half, we just divide by 4. So that's going to be 5.25. And let's double check. Yeah, so in this case, that's the position, but it's not 0.5, right? So up here, it felt like we had to go halfway because it was 10.5. Here is 5.25. So does it make you feel like you need to go a quarter of the way? Probably, but no. If there is a decimal, like afterwards, that just means half. In all cases, go half. So what does that mean? That we can find quartile 1 at the 5.25th position. Let's go. 1, 2, 3, 4, 5. And 0.25 means we go in between the next one along. So the midpoint of that is 5.5. Okay, so that's quartile 1. That's the median, or quartile 2. And our last one is to find quartile 3. That's going to be n plus 1 again. But we're looking for the third quartile. So if we found the first quartile and then multiplied it by 3, we would have 3/4 point. So there's a number of ways of writing this, and some people like to write 3/4 n plus 1. Well, doesn't really matter, I don't think. N plus 1 is 21 times 3 is 63 over 4, which is 15.75. Take a note of the previous one. Okay, so if I multiplied 5.25 by 3, I get this. So you don't need to do this calculation all over again. You can just look at it that way, as long as you know you're looking at position. Now let's take it from the beginning and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It does feel strange because I'm just counting and they're actually the numbers. Anyway, 0.75 doesn't mean you go to half. Sorry, it does mean you go to half. It doesn't mean you go to 0.75. So I'm not going to write 15.75. I'm just going to write the halfway point. That's a horrible error. 15.5. That's quartile 3. And there you have it. So if you've got a large number in your data set, it might be better to do it this way, because then you're not going to have to worry about drawing lines to find the middle point, where you might count from the outside in. And this is still a small data set, to be honest. The data set could be huge. And if we just count from the left, it's easier than alternatives. Okay, so do you think it changes if we have decimals? No, it doesn't. So here n equals 8, and so we can see visually again that we have something like this. All right, so the midpoint is in between here. So for quartile 2, we've got 5.8 plus 6.9 all over 2. And absolutely nothing wrong with the fact that this is a decimal. It's just going to turn into our answer as a decimal. And that's the same with the other two. Okay, so we're going to, this one would be 7.2 plus 8.3, and then divided by 2. And that's going to be 7.75. And down the bottom, I got the midpoint of the left-hand side. 3.5 plus 4.7 divided by 2 is 4.1. Okay, an interesting scenario. All the numbers are the same. What would you do? I say you should take a second. You could even pause the video, but they're all the same. Okay, so there are about 7 different ways that some certain professional statistical software will calculate the quartiles, and in all cases they say that this is how you do it. Now, just to be sure here, we have 7 numbers, right? 1, 2, 3, 4, 6, 7. So the middle number is 10, so that's medium, yeah. And that would be absolutely fine. Technically, when you have 2 numbers next to each other, and you wonder, like, what's... I'm going to give you an example. Let's say if I had 17 and 17, and I want to know what the midpoint is of 17 and 17, right? What's in between these two? And a lot of people, you'd be surprised, they say 17.5. You see how it doesn't make sense, right? Because you've got on a number line 16, 17, 18. And if you've got 2 numbers exactly on 17, what's in between those 2 numbers is still in line with 17. Like if you said that it was 17.5, that's up here. It's doesn't make sense, right? So what does make sense, however, is that the midpoint of 17 to 17 is 17. You can add them together if you want. Divide it by 2. What do you get? 17. But this is fine to say. Now on the right side we've got 10 again. Quartile 3 is 10. Ugh, but it can't be. That's the same as the median. Actually, it can be. So in this case, they're all the same. And it's just not very nice. It doesn't really help to draw a box plot. Okay, so typically box plots go like this. This box plot would look like this, wouldn't it? So it doesn't really tell you anything. 0 spread, but it tells you that there's 0 spread. I mean, that's what it is. Example number 7. Sum of 0. Does this make a difference? It doesn't matter. With a mean, you would add them all up, and so 0 would make no contribution. But this doesn't matter. 1, 2, 3, 4, 5, 6, 7. You've got n equals 7. So again, median equals the middle, quartile 3, and quartile 1. What about this? Minus 10, 5, 0, 5, 10, 15, 20. Sort of some negative numbers in there. Does it make a difference? Not really. When you look at them, even the mean is not terribly affected in this case, because things cancel each other out, sure, when you're adding them up. But you'll still get a good answer. And so as long as these are in order, even if it goes down to the negative, how many have we got? 1, 2, 3, 4, 6, 7. So that's still the median. That's still the quartile 3. And that's still quartile 1. And here for the last one, well, the last two, I'm going to invite you to have a go on your own for number 9. Ideally pause the video, but you should be okay. You start by n equals 7, so we know how many you're dealing with. Visually, we have a center point and 3 either side. So quartile 1 is 3, quartile 3 is 9, and our median, also quartile 2, is 6. Okay, so now we're at example number 10. I've realized that there is an error with this question. I didn't update it, but here we go. We're going to change it. So essentially, we want to find h. So have a go. Give yourself pause of the video and good luck. Okay, I'm sure you did absolutely great. Let's have a go. We know that from the structure, we have an even number. So the median is located in the center here, in between 10 and h. So we know that if we did 10 and we add h and then divide it by 2, that would give us our median. And we know the median is told to us is 13. So we have to now rearrange to find the unknown which we're trying to find, which is h. It's the only unknown in this equation, which is great. So we used a definition, and away we go. 10 plus h equals 26. That's multiplying both sides by 2. And then h is equal to 16 if we take away 10 from both sides. And a quick verification will show that that makes sense. So there you go. So you will move on to not just doing these things, but a bit of problem solving and using the definitions to work backwards. Your next steps for exploring the medians and the quartiles is going to be finding them inside frequency tables. And that requires a slightly different method, and it gets a little bit complicated when you're interpolating, for example, estimating the median if you have ranges instead of nice numbers like we have here. So that's a step up if you want. And thanks for watching. I hope it was useful.